Okay, we continue. We go to design flow now. What we will do uh, in this semester is basically based on this flow chart. We call it design flow. So from the design specification, right? So we will use here design. We will select the design entry, and normally we have two type of design entry. The first one is schematic capture, where we draw the gate and so on, the module and so on. So in this course we will not using schematic capture lah. This one is suitable for small design, but for bigger design we will use the language where we will use Verilog or in some in other courses maybe we use HDL can also, but the flow is the same. We use language, Verilog, hardware description language, and after we write the code we will synthesize or synthesize our design, and we will check whether the design is correct or not in terms of functionality. We call it uh, functional simulation, and if it is no problem we proceed to the next step. If we have problem with the output, means that it is not function according to our specification. For example, we want the output to be 1 but we get 0, for example, right? So means that something wrong with our design, so we need to go back and we do the code and synthesize and do the simulation again until everything is good here. We get the correct output, and now we do the physical design. Physical design means that we map to the hardware that we want to use. So if you look at in the market, we have many type of FPGA that we can use. So in the software later on we will see the FPGA that we can use in our design. So that FPGA has different properties, characteristic. Means that some of the FPGA is good, fast, right? Some of the FPGA is slower, right? So that when we select or choose the hardware that we want to use or FPGA that we want to use, we call it physical design. And with that, we need to do what we call the timing simulation. We will see whether our design meet the timing specification or not. For example, we want our design to be very fast, but we use the very slow FPGA. So when we run the timing simulation, sometimes it may violate our timing. Means that the we will get the wrong result. Result, although we have the functional simulation here is correct, because functional simulation here it will ignore the timing, the timing. But in practice, timing is very important, because the signal travel from one node to one node has delay, signal delay. So if we uh, our system is our FPGA is slow, but we in our design we use a very fast input, means that our input is changing faster than our FPGA, then we may get wrong result, wrong output. So this one is very important. And when our design pass the timing simulation, then we can do the actual chip programming, which where we transfer our design to the actual chip, actual chip. But if not made this timing, we need to go back to redesign and look at the design again, whether we can improve the time, the speed, the performance or not, in order to meet the timing, right? So that is design flow. Now we come to the modeling style. So before this, just now I just introduced to you how we write Verilog program to describe the circuit. But actually, the way that we write the code belong to the what we call the type of modeling or modeling style. So some of the code that I show you belong to what we call the data flow modeling. Some of the example if actually in the behavioral modeling, and some of the example is from structural modeling. So what is data flow modeling? So the data flow modeling is specified in terms of input signal transformation based on Boolean expression. So when we use Boolean expression and we describe our circuit using continuous assignment statement, that means we use data flow modeling. All right. So remember, you need to be able to differentiate or to know this. When you use continuous assignment statement, for example, you use this thing. This one is continuous assignment. All right. And of course, when you use continuous statement, you will use the Boolean equation. And when you have this means that you use data flow modeling. Right. Remember, when you use Boolean expression and describe your circuit using continuous assignment statement, means that you use assign keyword. This means that you actually using or design your circuit using data flow modeling. But when you use or describe your circuit using behavior of the circuit, and you use sequential or procedural assignment statement, means that you use your code or you write your code this way, means that you design your circuit using behavioral modeling, right? And the last one, if you describe the structure of the circuit in terms of circuit elements such as logic gate, or a larger circuit is defined by writing code that connects such element together, that is called structural modeling. For example, when we design using logic gate like this, and we describe the connection. Z1 is here, X1 is here, X3 is here, and this one is Z2, like this. Gate instantiation is actually structural modeling. So there will be three modeling style in Verilog. All right. So now the question is, which one you need to use in order to design your circuit? The answer is can be either one, or combination of two, or combination of three, depend on the type of the circuit that you want to design. For example, if you have the circuit already, right, the schematic already, for example, like this, yeah, you have the schematic already, and you know every connection here, and you can use the structural modeling, right? But if you don't have your schematic, but you don't but you have the Boolean equation, for example, you can describe using data flow modeling or behavioral modeling. All right. But if you use behavioral modeling, you need to describe the Boolean equation inside the always block. All right, because you need to use sequential assignment statement. And if, for example, you don't have Boolean equation because the specification is a little bit complicated, all right, you don't even have a Boolean equation, and you don't even, of course, you don't even have uh, the schematic. So you need to use behavioral modeling using behavior of the circuit, right? So that is where you need to implement this modeling style. But sometimes you need to use combination of this modeling. Sometimes you need both. Sometimes you need all the three. Depend on the design that that you want to design. And of course, will be depend on experience also. When you start to write your code, you do many times, you need to you will able to figure out already what kind of modeling that you need to use for some for a particular design, right? So let's again look at the example for the first one, data flow modeling. So you have been introduced to this already actually in the previous example when we use assign keyword. All right, that is actually data flow modeling. All right, so for example, we have this schematic, and we can have the Boolean equation of y0, right? Where y0 is actually equal to en n x1 bar n x0 bar, that is y0. So here we use assign y0 equal to not x1, here, and not x0, and en. We get y0. And for y1 is not x1, this is x0 and en, and y2, y3, and so on, right? So this will be data flow modeling. We also can describe this circuit using structural modeling, right? Because we have the connection. But before that, let's look at the second example here. This also the data flow modeling. The circuit is for half adder. I think you know already what is a half adder. You should learn this in digital electronic before. So the half adder comprises of one XOR gate and one AND gate like this. So S is equal to A XOR B, right? And we use assign keyword. Assign C equal to A and B, right? And we get this circuit. And this is data flow modeling. Next is another one, with the full adder here, where we have two XOR gate, this, and we have 3 AND, we have another OR here. And we can describe using data flow modeling easily because we have the equation S is equal to A XOR B XOR C, Ci. I forget I here. So yeah, so we need to have Ci here, right? Ci. And for CO is very easy. This one and this one, and we all together to get C. So this is data flow modeling. And let's look at the behavioral modeling. Yeah, and again, you have been introduced to behavioral modeling already before this, where we use the sequential statement, and of course, if we use sequential statement, we need to use always block. Yeah, we need to describe the circuit in the always block. So, for example, here we use if else statement. So if x equal to 0 and y equal to 0, z equal to 1. All right. So this is behavior. So this is the full code, and this is actually an OR gate, right? When x equal to 0 and y equal to 0, both x and y equal to 0, z equal to 0, but else z equal to 1. So when we look at the behavior of the OR gate, all right, So we have what is the input? We have X and Y and Z. The output is Z. So the OR gate is this X, Y, Z. So we see 0, 0, 0, 1, 1, 0, and 1. So the OR is 0, 0, we have 0. And other than that, we have 1. All right. And see, the behavior is that if X and Y equal to 0, Z should be equal to 0. Other than that, we call it else, right? So this is if Z equal, if X and Y equal to 0, both of these equal to 0, Z should be equal to 0. Else means that other than this, Z should be equal to 1. So this is the code. If X equal to 0 and Y equal to 0, Z must be equal to 0. But other than that, Z should be equal to 1. So this will be translated or synthesized into an OR gate. And again, the Z must be declared as rect. Remember? So we can write like this, output rect Z. Z. And look at the second one, where we have AND gate, right? So this is the behavior of AND gate. Where we have zero, 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 1. Okay. So Z equal to 1 only if X and Y equal to 1. Else, Z should be equal to 0. So only if X equal to 1, Y equal to 1, then Z equal to 1. Else, Z equal to 0. So this will be the AND gate. So this is behavioral modeling. What about structural modeling? Structural modeling we have learned already, actually, where we instantiate the gate and do the connection. That will be structural modeling. And these all are the gate then we can use in defining the circuit using structural modeling. We can use structural modeling using for not only for gate, for module also can be used. Module means that our previous design. When we want to use our previous design in a new design, we will use structural modeling as well. Okay, so this is another example. The half adder so can be described using structural modeling as well. XOR as AB, AB, and C output AB. Then we get the half adder circuit. All right. So that is design modeling. So remember, we have 3 design modeling. The first one is data flow modeling. The second one is behavioral modeling, and the third one is structural modeling. All of these we will use a lot in our course later on. All right. Any question before we go to the next? I think okay. I think it is straightforward. And now we go to synthesis of design. Synthesis of design means we translate from the code to the circuit, to the schematic, to the circuit. Uh, this is actually uh, done by the software. The Verilog compiler will do the synthesis task for us. We as a designer, we write the code and let the computer to synthesize the code to produce the circuit for us. But we as a designer need to learn this. We need to know, if we write the code this way, what kind of circuit the computer, the Verilog compiler, will produce for us. All right. So uh, by knowing that, we will be a good designer, because we know how which part that can be optimized, which part that can be modified in order to get the best design. Okay, so again, from the code, we should be able to know what is the design or circuit that we will get when we write the code this way. So the first one is using the data flow modeling. We have assign x equal to this. So this is a very simple Boolean equation, and we have the equation, and we know exactly this is the circuit that we will get if we write this way, right? So we have x not is actually not A XOR B, right? This is A XOR B not, and we get X. And Y is X and C, so this is X and C and OR with B, and we get Y, all right? So meaning that this code will be synthesized into this circuit. Second one is the same circuit actually, but this one is using the structural modeling, right? Where we instantiate the gate, and same thing, we will get the same circuit, right? And of course, here we need to label the signal here, all right? This one, no need to label because we have the relation between X and AB, but here we need to label because we want to do the connection between this, and this. Not gate. So we need to label T1 or any other name, depend on you, right? In this case, this one is T1, so C XOR. T1 is the output AB, and this is not gate. T1, the output is X, so X T1, and this one is this, and we have T2 here, and we have Y. So same circuit, but by using structural modeling, we need to label here. And here also we produce the same circuit, but in this case we use the behavioral modeling. All right, very easy to observe. Behavioral modeling, we have the always block and always block here. So this part will generate which part we need to look at this. Yeah. If A equal to B, T1 equal to 0, and this is if A equal to B, T1 equal to 0. What is that? If A equal to B, T1 equal to 0. So where is T1? T1 is here. So must be this one, right? AB and AB must be this one. So if we look at this behavior, if A equal to B, T1 equal to 0, else T1 equal to 1. So if we look at the behavior, it's something we have A, B, and T1. The code says that if T1 equal to, if A equal to B, T1 equal to 0. If A equal to B, where is it? If A equal to B, here. A equal to B, 0, 0. And here, 1, 1. So T1 equal to 0. Else, T1 equal to 1. Alright. So this is the behavior of XOR gate. right? That's why this one will be synthesized into an XOR gate, and X is not T1, all right? X is not T1, so you get X and you get not gate here. And for this one, a little bit tricky, right? Where if X and C or B, then Y equal to 1, else Y equal to 0. So must be this part, because we have XCB, XCB, all right? So this part will be synthesized into this gate, all right? So go back and try to figure out how this code will be synthesized into this one, all right? That is your homework, your exercise, all right? And you can see that synthesize the behavioral code is not easy as compared to data flow and structural, because structural can be directly mapped to the gate, and also the data flow. All right, the Boolean equation is directly mapped to the gate, but behavioral code is not that easy, right? We need to understand this and create this, right? But this is very powerful method, because normally we don't have this, and what we have is the specification, all right? Okay, so go back, try to do this. Yeah, I want to give you one example, another example, which is not in the lecture note. Let's say we want to design something like this. Uh, we have a very simple application. Let's say that we have an office or room. Let's say we have 3 doors in this office. One here, maybe another one is here, and one is maybe here, one here, another one is here. And let's say we want to have a monitoring system that to uh, observe or to monitor the door. If 2 or more doors are open at the same time, all right, it will trigger the alarm. All right, so we want to make sure that at one time only one door is open. Okay, so let's say we have a sensor at this door, and we name it sensor A. This one is named sensor B, and this one named sensor C. Okay, and we have, of course, an alarm here. So our specification is that if if 2 or more doors are open at the same time, alarm will be triggered. So what is the best way to create the circuit, the controller that read the signal from the sensor? So for example, if door A is open or door B is open, the signal for door open is A equal to 1 to indicate that door A is open. Yeah, open. All A, B, C, if equal to 1 means that open, and if equal to 0 means closed. right? Now we want to design a circuit that doing just this, where we have input A and we have input B and we have input C, and we only have one output, the lamp, uh, let's say F, right? So a lamp is, or F equal to 1 when either 2 or 3 of these is equal to 1, right? So the question is, what modeling style that we want to use in order to model or create or design this circuit or controller? We can say that. Any idea? Nabil, nak jawab Behavioral Syamil kata behavioral. Any other than that? Tak ada. So Syamil says that behavioral modeling is the best way, and I do agree with Syamil, because we don't have circuit, right? We just don't we just have the behavior of this. So the best way is maybe we use the behavioral modeling. But actually we can use data flow modeling, where we can actually derive the Boolean equation, right? Because we only have 3 input and 1 output. 3 input, 1 output is easy. All right, we can still manage to derive the Boolean equation. So we can use data flow modeling, all right, where we need to derive the Boolean equation first and we design the circuit. Or we also can design using structural modeling, because again we can derive the schematic for this. Again, it is because the circuit is relatively small, 3 input 1 output, we can derive the Boolean equation. But let's, for example, if we have more than 3 input, we have 5 or 10 input, right? Just imagine how to derive the Boolean equation. This is almost impossible now, right? So the best way is to use behavioral modeling only, right? But this example you can use either one actually. The easiest way is to use the behavioral modeling, because you can straight away create the behavior of this. So you can write the program, Verilog program. We can start with module. Circuit name is let's say alarm. Can you see this? And we need to list all the port, so that we have A, we have B, we have C, and we have F. Input, and input in Verilog must be in lower case. I must be lower, small I, cannot use capital I. Remember, Verilog is case sensitive. So input, we have A, we have B, we have C, and we have output And this output, because we want to use behavioral modeling, of course, we need to use always block. And again, if f is to be assigned something to f using behavioral modeling, so f must be declared as rect data type also, and this one should be f. Okay, and now we can start our always block, and in the bracket is called sensitivity list. What is sensitivity list? Sensitivity list is the list of the signal that will immediately affect f, or f is sensitive to what signal. So in this case, f is sensitive to all the input a, b, c, a, b, and c, right? F is sensitive to all these signals. Whether A or B or C change, it is immediately change F. Okay, or immediately affect F. Okay, so that means A or F is sensitive to A or sensitive to B or sensitive to C. Or you can write this way, in Verilog, you can write A, comma, instead of using O, comma, B, comma, C also can be used in Verilog, no problem. All right, so sometimes I will use or, sometimes I will use comma. Right, so don't be confused. Both style can be used. Now, we can describe our circuit now. So we can say if A and B, all right, because either one is 1. So A and we use logical AND now when we use if. All right, if A and B is true or equal to 1, or A and C is equal to 1, all right, though A and B open, or A and C open, or another one is B and C open at the same time, or the last one, all the three are open. All right, so if either one is true, F must be equal to 1, else F must be equal to 0. And at the end, you write N module. So this is the behavioral modeling of this application. All right. Or you can derive the Boolean equation for this, because this is easy. So you can have straight away derive the Boolean equation actually, because the specification is clear, where we have F should be equal to A, B, or A, C, or B, C, or A, B, C. Okay, A, B, or A, C, or B, C, or A, B, C. And we can simplify this equation, right, where we can factor this, because we have AB here, AB here, we have 1 here, and C, this is 1, C, and this one we can factor also, and we can get something like this. And in logic, 1 plus C, we have of course we have always 1. Yes, so this one we can get AB or C, A or B, C and A or B. So this is the simplified or the optimized circuit. So we can use a sign rather than this one, yeah, rather than this one. This one, this one, this one, this one, this one, this one. So we use a sign. So a sign F equal to A and B or C and A or B, right? So we can get the same result also, or maybe you can if you cannot derive this, you can start with the truth table, right? You can have the truth table for this A, B, C, and then your F. Okay, list all the possibilities because we have 3 input, so we should have 8 possible combination input, yeah, input combinations. And based on our specification, if one or more signal here equal to 1, then the output should be 1. So this one is of course no, because all are closed. This one also no, right, because only 1. This one no, because only 1. Yes, this one yes, because we have 2 open. This one only 1 no. This one 2 2 3 2 and 3. Okay, so this is again, this is actually, if we take the sum of product, so this is BC or AC or AB or ABC, right? Or we can have the K-map. We have A 0 1, A bar and BC here 0 0, B bar C bar 0 1 1 1 and 1 0. And let's see if BC is 1 1 and A equal to 0, we should have wait, yeah, here if 1 1 here 1 1 1 and 0 1 1 and 0, we should have 1. And if here A is 1 and 0 1, should be here 1 0 1, so we should have 1 here, and here 1 1 0 1 1 0 1 1 0 should be here, and the last one is 1 1 1 1 1 1 should be here. And when we map, we can get something like this. This map to this, this map to this, and this one map to this, and the last one is here map to this one. Or maybe I used a different color. Okay, looks better. Right, so this term is what is this? This one, it should be A, C. This term should be BC, and this term should be A, B. So you have F equal to BC, and this one is AB. And at the end, you will have F equal to BC plus AB plus AC, which is actually the same as the previous one, which is AB plus here means or, yeah, AB or C A or B at the end. All right, so we will have the same as this one, this, right? So either one you can use, but the easiest way is to use, yes, of course, the behavioral modeling. Yeah, straight away from the specification, because we know the behavior of the circuit, then we can produce the code very fast. Okay, any question? Yes, Shamin. Okay, 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 got it. You see here, especially this one, we have to always block, and here we have begin, and this one we don't have begin. All right, so the question is that compulsory to have begin? Depend. If we have, for example, this one, how many statement we have? If we have more than one statement, we need to have begin and end. For example, here we have two statements. All right, the first statement is if else. This is one statement. This is another statement, x equal to not t1. Means that we have two statements here, two different statements. So you need begin and end to tell the compiler that always block will include this one and this one. But if your code in your always block, you only have one statement, all right, because the line after the always block is always inside the always block. All right, but if you have many line after the always block, you need to specify your always block start from where to where. So in this case, you have only one statement actually. If else statement, this is considered one statement, right? Because this one is actually in the same statement, right? If this do this, else do this. This is one statement. All right, but this one is different. This one, if this, do this, else do this, one statement. Another one you have x equal to t1. All right, or I give you another example. We have always block, right? And of course, we need the sensitivity list, right? Can be anything inside there, right? So I have f equal to a or b. That's it. So do I need the begin and end? No need, because this one is considered inside the always block already. The computer know, the compiler know, the line after that, after this always block is this statement, and this must be in this always block. But if I have another statement, I have g equal to m plus, and this is not O, sorry, this is m minus n. Then here is wrong already, because the compiler only know that this one is inside always block, but this one should be not inside the always block, right? So to tell to the compiler that both statements are inside the always block, so we need the begin and end. So we need a begin and end here, right? To tell the compiler that my always block is comprises of this and this. Just like in C programming, when you have, for example, you have for loop statement, right? So you write for, yeah, I equal to 0, I less than 10, I plus plus, and next you have AI equal to 1 plus BI, for example, 1 plus BI. So in C programming, when you have for statement like this, and you have only one line after this for statement, so no need to have what we call the open statement here, right? But if you have two, you have CI 1 plus ZI, for example, then you need to close here. Means that these two statements are depend on this for loop. Okay, same as this one. In Verilog, we use begin and end. In C programming, we have this curly bracket to open and to close, to begin and end. Okay, Shamim? Okay, welcome. Okay, so we are here in synthesis of design. I think just a little bit more to complete the chapter, and we have another half an hour. Any other question? Okay, so if no question, I think we will continue the remaining part of the chapter next week. But before we end the session, I want you to download the software that we use in this course. Okay, So you need to download the software and install in your computer and try to use it. Yeah? I will share the tutorial that uh, the video tutorial video that I created last semester, so that you can use the software, the software to write the code and try to simulate the code. So in order to download the software, yeah, and the software is quite big, more than 3 GB, the size of the software. So you need to go to the internet. So you can type Intel Quartus Prime download. Okay, you can search for Intel Quartus Prime download. All right, it will bring you to the Intel website. And I think this one, the first one, just click this. Okay, so you will have the software which you can download and use for free, but not all edition are free. For Pro edition, you need to pay for the software. Standard edition also need to pay, but this one is free. Download free, no license required. Light edition, and this is sufficient for our learning. All right, so you can go to the light edition. And this is the latest edition, 20 release 20.1.1. You can use this edition or any other edition, which is no problem actually, right? You can download, combine file. Yeah, I suggest you to download combine file. And what you need to download is Quartus Prime, this model sim. These two must be downloaded. These two software must be downloaded. All right, model sim is used to simulate your design. Quartus Prime is used to write the code, right, to design. This one is to design, this one is to simulate, for simulation. And for the device, you need to download, I think should be either one enough, because this one is actually based on what hardware that we have. That in the lab, actually we have Cyclone 2, and this is Cyclone 4. I'm not very sure whether we have Cyclone 4 or not. Later I check, but I suggest you to download Cyclone 2 for the device. All right, don't download all, because the size is very big, especially Cyclone 5, 1.3 GB. So Cyclone 4 should be okay already for learning. All right. So the hardware that we have, I think we should have Cyclone 4, and we actually have many Cyclone 2. So I use of normally I use Cyclone 2, but because this latest release not support the previous hardware already. But if you choose, for example, the previous release, so you can have Cyclone 2, 3, 4, and so on. All right, so this one we have the hardware and the FPGA that can be used, the actual FPGA, the actual chip. So we have, but for simulation only, we can you can use any release, right? So before this is 20 point. Okay. 20.1.1. There are 20.1.1 here. Okay, so you download three files. First one is the quarters prime. Next is the model sim, and cyclone 4 for device. And when you install, you need to install this first, quarters prime first. When you install, you will be asked to install this during the installation. So just install and select the file that you download. And also you need to you will be asked to select the device. So make sure that all three files are available in the same folder before you install. All right, then you will be okay. All right, so next week I will show you how to use the software. So maybe we can use together, right, to design or to do some simulation, a simple simulation for simple design. And I may give you a quiz next week through using author. All right, chap topic will be what we learned today. Okay, that's it, I think, for today. If you have any question, then you can ask through Telegram. Okay, so all right, it's no question, we stop here. Thank you.